So in today's lesson, we're going to be taking our function topics and really focusing them on linear equations. And the rest of this unit, we're really going to focus our attention on three different forms of a linear equation. But we're going to start with probably hands down our favorite, which is what we call slope-intercept form. So there's two good news here. First of all, it is probably the most user-friendly version of a linear equation. It is very informative. It gives us some really key pieces of information just at a glance without us having to really do work for it. But also, it really is in that function type of relationship, and it's familiar to you. You have worked with this equation before, last year in math. I am certain if you went through 8th grade math as a pre-AP 7th grader, you know that one of the most common ways of writing a linear equation is that y equals mx plus b. So that's what we refer to, or that's what we're referring to when we say slope-intercept. It's called slope-intercept because simply by looking at it just at a glance without us having to do any work, we can see right away what is the slope of the line. That's always that coefficient that is attached to the variable x. And it also tells us what is the y-intercept of the line, which is really the two major characteristics that define a specific line that make it unique, is how steep it is and where is it located. So it gives us a steepness and a location right away, just with our eyeballs. That's all we need. We don't have to do much math if it's already in slope-intercept. Okay, so other characteristics is y is isolated, and everything else is on the other side. And that's another reason why we like it, because it does have that kind of function input-output relationship type of setup, right? Where we plug in here into our input and the outcome is already isolated. That's our output over there. So it relates to the functions that way really nicely, okay? So we're gonna do some reviewing of concepts you've already learned, but it might have been a while. We're gonna talk about how to find the slope of a line, how to use slope-intercept form, which is this guy right here, and how to use slope and y-intercepts to, solve real life scenarios or word problems, that sort of thing. Okay, so let's review slope. Okay, so when we're talking about slope, slope is essentially a numerical way that we measure how steep a line is. It gives us the rate of change between any 2 points on a line. Okay, it is a measure of its steepness. Okay, so slope is just a numerical measurement of how steep something is, or a line is, and we measure it as the rate of change between any 2 points. Okay, now to find the slope of a line, we write it as a ratio. Remember, that means that we're comparing by division. We find the ratio of the vertical change, also often referred to as the rise of the line, okay, and compare that to the horizontal change. A lot of times we refer to that as the run of the line, okay? So slope, we can think of that then as a ratio, vertical change over horizontal change. Vertical always goes on top. That is absolutely non-negotiable. It'll never be different. So the vertical change goes on the top, the horizontal on the bottom. That's not how you spell change. Let's try that again. Okay. And you very likely will have seen this and recognize it, just a shorter, quicker way of saying the same idea, rise over run. That's how we essentially measure that steepness or that slope, is a rise over run. So on the top here, we're going to be measuring how far we went vertically up or down. That's what we call the rise there. And then the run is how much we are moving horizontally, okay? Sometimes we refer to this as well, change in y, that means change, delta, over the change in x. So if that looks familiar, that is good news. I know you've done this before. We are just refreshing our memory about it, okay? So you have a good example here. If you have a line, the idea is you could pick any 2 points on that line, and really it doesn't matter what 2 points you pick. However, it's one of those things, it doesn't matter, but it does kind of matter, right? So it doesn't matter. Mathematically speaking, you should get the same slope no matter what points you select. However, because we're human, right, and we have some, limitations in terms of how accurately we can estimate things, I wouldn't want to pick a point that's kind of floating out there in the middle of two whole numbers, because then I really don't know its exact location. If I knew its exact location, then it would not matter whether or not, what point we picked. But because, we're doing this by hand right now, pick points that you see land nicely on whole numbers so that we can really count that rise and that run accurately in whole units. It's going to make your life a lot easier. So when I look at the 2 points that we picked, the next part is measuring the rise and the run. So I would ask myself, well, how many units did I go up or down? And in this case, to get from this point to this point, I would have to go up 1, 2, 3 units. So that's a rise of 3. And then I would have to go to the left 1, 2 units. And that's a run of 2. So that's your rise over run. They wrote it on this side. It doesn't matter if you write it above it or below it, but the values are the same. You have a rise of 3 units over a run of 2. That gives you a slope of 3 over 2. So another reason, remember I was team fractions from day one, right? This is another reason why I really like fractions. We do a lot of work with linear equations and slope, and let me tell you, fractions are actually great news when you're looking at a slope, because when you go to graph lines and work with them, you always want to know what those two movements were. So seeing a fraction is actually a welcome sight, good news, because it immediately is going to be like, oh yeah, this is telling me exactly how much am I moving vertically and how much am I moving horizontally. Okay. All right, so let's practice this real quick. We're not going to necessarily, go through this very much in detail. I know this is just review. In an equation, I want you to be able to spot it and look, see the equation and spot what that slope is, okay? So if I look at A, we did that one together as practice. Describing the graph here, the idea is starting, the y-intercept is at 3, and then it's a negative slope, so it's falling from left to right because it's a negative slope, that's why. So from left to right, this line is going downward. And in fact, if we wanted to be really specific, we could say it's going down 2 units over 3, down 2 units over 3. That's what that rise over run tells us. And then really being able to just pick out the slope and the y-intercept, knowing which one of those is the slope M and which one is the y-intercept B. Okay, so you could even think of it this way if that helps. Okay, and then let's try the next one. So for this one, if I'm going to let's spot the slope and y-intercept. Let's focus on that. Y equals 2x minus 2. The slope here would be the positive 2. And if I was actually using it to graph, I might actually want to write that as 2 over 1. I'm not using it to graph right now. Well, actually, I am. We're going to graph it in a moment, so you're going to see that. So I am going to use it. Our graphs are right down here. So I might actually want to write that whole number as 2 over 1. That's how much we want this to be a fraction, because we really need to know both movements. Okay, we want to know what was the vertical movement and what was the horizontal movement, the rise and the run. So this might be more helpful when we start graphing, but both of those have a slope of 2. So that is our slope. That is what was attached over here with x. And then our y-intercept is negative 2. Okay, this guy right here, if I don't see anything in front, it's automatically a 1. And if there's a negative, that means our slope is negative 1. Or, since I'm about to graph this, negative 1 over 1. Okay, if it's a whole number, you're going to put it over 1. And then our y-intercept here was 1. And this guy right here, for D, the slope, I don't see anything at all. That's the slope of 1. And if I write that as a fraction itself, and then our y-intercept is at negative 4. So then let's review how we're going to then graph. So I always tell my kids, for a long time, I was kind of puzzled. Why would they pick M and B for slope and y-intercept? Okay, and then a light bulb went off, and I don't know if this is really what they meant to do, but I think it's worked out really well, for me at least, and for my students. When we're looking at y equals mx plus b, one of the ways I always remember how to graph this and why I suppose maybe they used M and B is because the B value, the y-intercept, will always give me a point where I can begin my line. So I always remember B is for begin. You're going to begin at that point on the y-axis. That tells me a beginning point, okay? So that's always going to give me a number or a place for me to begin my line on the y-axis. And then once I am at that point, the slope is going to tell me how to move so that I can get to the next point on the line, okay? So let's try that for A here. It has a slope of -2/3 and a y-intercept at 3. So what that tells me here is that I can come to my graph, I can find where y is equal to 3 on the y-axis, and I know that when I'm there, I'm on the line. So that is where I'm going to begin. I'm going to begin where y is equal to 3 on the y-axis, because that was the y-intercept here. And then this is going to tell me how I'm going to move. The slope is -2/3. So that's a negative. That means my rise, remember up here, I like to attach the sign to my rise and go up if it's positive, down if it's negative, okay? So I'm going to begin at 3, and that slope is telling me that I'm going to move down 2 units and over 3. So I'm going to go down 2 units and then over 1, 2, 3. Be careful not to do a double negative. If you go down and backwards, you basically did a double negative, and you're going to end up back at a positive line. So if you moved down, then you've already essentially used up your negative number. Make sure that your run still goes in the positive direction. Okay. Now I want to always plot 3 points, and I don't really have room here. So this is an excellent time to share with you that you do have the other option of attaching that negative to the denominator instead, to the horizontal move. And I could have moved up +2, but then backward 3. There's my negative move, right? So I go up, which is positive, but backward, and I'm still on that same line, right? So now I can go ahead and take my straight edge and all these points. This is why you always want 3 points, because it's a great confirmation. If they all line up, then you know you did it correctly, okay? And it avoids any mistakes like that. So if you did it right, they're all aligned. And see, I got to the same location or to the same line whether I went down and forward or whether I went up and backwards. I only did one negative move, and the other one was a positive move, right? I don't want to do double negatives, because then it becomes a positive line again. So either down but then still forward, or up but then backward, and I'm still okay. It's still a downward sloping line when we look at it from left to right. Okay. Let's go to this guy. It tells me the y-intercept is -2, so I'm going to begin at -2. And then my slope is 2, but I really want to remember that really means 2 movements, 2 over 1. So that means a rise of 2 units and over 1. Rise of 2 units over 1. At least 3 points, if not more. If you do that slope correctly, consistently, you should get all of those points nice and aligned, and then you can graph the line with your slope and y-intercept. So you can see this is really why we like this line. It's very informative, gives us those really important pieces of information, lets us graph it quickly. It's all good, okay? Let's try the next one. This one has a y-intercept at +1 for C. So here we are on y-axis at 1, okay? And then if we start here, this is our beginning point, and we have a slope of -1, that means down 1 over. So again, I could go down 1 and then still forward, down 1 and still forward, down 1 and still forward. I could go up but backwards, as long as one of your movements is a -1 and the other one is still positive, you're going to get the correct line. So a positive slope, I certainly would expect this line to be going downward from left to right, falling down, and it is. So we're good here. There's my line that has that slope and that y-intercept. So that's exactly the line that has those characteristics. That's like its fingerprint, right? So when I think about slope-intercept, I'm like, that's kind of the fingerprint to that line. There's only one line that's going to have those characteristics. That's what's kind of neat about it. It's kind of like its social security number or its fingerprint. It is unique to that line, okay? And then last one here, it has a y-intercept at -4. So I'm going to begin on the y-axis at -4. The slope is +1. So that means up 1, forward 1, up 1, forward 1, up 1, forward 1. Rise over run, rise over run. So 1 over 1. And so my line is over here in the corner. And then we can connect. Okay, so hopefully that was just a nice review over slope and the fact that it's a ratio of rise over run, and then how to take something in slope-intercept and be able to pluck out the slope in the y-intercept and use it to graph the line. Okay, that should all be sounding pretty familiar. Okay, so let's flip it over. All right. Here we're kind of working a little bit backwards. It says find the slope and the y-intercept of each line, but they labeled it for us. So it's nice to see the line, and maybe you could test trying to do this without the equation being there in front of you. But from the equation, you can pick out those two pieces of information as well. So they want to know what is the slope of the line and what is the y-intercept of our line here. Okay, so I can see my graph is intercepting here at 1 to at positive 2, and that's confirmed here on the equation. So my y-intercept is at 2. And then the slope, according to the equation, is 2 over 3. Let's find out. From here, if I go up 2 units, and then to the right 1, 2, 3 units, oh, yep, sure enough, I land on my line again. So there's that rise of 2 units, and that run of 3 units. And so that's why our slope is 2/3. Okay, so even if that weren't there, I would want you to be able to look at the line and be able to identify that y-intercept, and then identify another nice kind of point, and then identify, okay, what was my rise and what was my run. So here I would have to go down 2 units over 1. Okay, so for this one, the slope, and that's confirmed with the equation, so that's kind of nice to have there as a confirmation. Y-intercept then is -1. Okay. How can you describe the graph of an equation written in this format, right? So if we talked about just a generalization, what do we know about what those meanings are? How does the value of m affect the graph? Well, remember, it measures the steepness, right? So the value of m determines or measures the steepness of the line, right? So determines, so let's say m determines or measures the steepness of the line. That's its job, right? And then for b, how does the value of b affect the graph of the equation? Well, b is the y, it gives the y-intercept. Okay, gives us a location. Right, so this measures the steepness, this measures or denotes what the location is. Okay, all right, so now that we've talked about that, we're going to formally talk about the equation that's written in y equals mx plus b is in what we call slope-intercept form, because those are the two pieces of information that it gives us just at a glance, right? So that's slope-intercept form, where m is the slope, we're just reviewing now, and b is the y-intercept. Okay, so it's always where does it intersect the y-axis and how steep is our line. Okay, so if we practice just a couple of here that says find the slope and the y-intercept of each one of those, as long as you know what characteristics to look for from that equation, this should be pretty simple, right? So if we want to identify the slope and the y-intercept, as long as we know where to look here, we can see, hey, the slope is always going to be attached to x, so that is going to be -3/4, and the y-intercept is going to be the number that is added or subtracted, but it's not connected to x. That's 2 in this case. That's your y-intercept. Okay, for this guy, the slope is always connected to x, so that would be the 5. The y-intercept would be the number that is added or subtracted and not connected directly. And if I don't see it, that must mean it is 0. Okay. This one, whoa, curveball. I'm really only able to look at these and see them off the bat if I'm in slope-intercept. right away, as soon as I looked up and looked at number 6, it hit me. I was like, that is not in Slope-Intercept. Slope-Intercept has a specific format. Y is completely isolated. Everything else is on the other side, and it's simplified. Okay, so for this one here, I cannot just look at this and say, oh, the slope is this, or the y-intercept. The slope and the y-intercept are not kind of revealed or available here just by looking. I have to solve for y to really uncover and reveal what they are. Okay, so we're going to rewrite this so that it is in slope-intercept form, and then we can decide what those are. So I'm going to move the x term, because again, slope-intercept has two qualities. Y is isolated and the right side is simplified. So I'm going to move the x's by doing negative 6x on both sides. So now I've got a negative 6x on this side with the 24. And then I'm going to divide by 4 so that y is totally by itself. Do not forget, you have to divide all of your terms. And now we are in slope-intercept. Y is by itself on the left side. Here I have negative 6 over 4, which does simplify to negative 3 over 2. But do leave it improper. This is one of the reasons we really like having improper fractions over mixed numbers, because so many times what we're talking about is slope. We just want to be able to see the rise over the run. So do not worry or bother with making that a mixed number. And then 24 divided by 4 happens to be 6. Now I can look at this and be able to tell, oh yeah, okay, so now I can tell from this format I could not, but here I can tell you with confidence the slope is negative 3 over 2 and the y-intercept is 6. See, those were not really there for us to see and know that on the original version. We had to rewrite it like this in slope-intercept to be able to see them. Okay? All right. So, finding slope, okay? Slope continued, right? So the slope m of a non-vertical line that passes through any two given points, okay, is the ratio of the change in y, otherwise known as the rise, to their change in x, or in other words, the run. This is how we started this conversation, right? So these are all synonymous with each other, okay? Slope, most often used with m as the variable, is the change in y, which we often call the rise, over the change in x, which is the run. When you have two ordered pairs, sometimes we don't see the graph in front of us. It's real easy to kind of, use on the ground the squares up and over. But sometimes we don't have that in front. What we have is ordered pairs. And then what we do is use the slope formula. Okay, this should also look familiar. So the way that we calculate that rise or that change in y is by doing the difference between the two y coordinates. How much did that y value change? That is the algebraic or mathematical way of doing what we do on the graph of just counting squares, right? We're like, oh, we went up 2, 3, or, we went down 4. When we don't have that picture to just count squares, we simply subtract or find the difference and say, okay, well, how much did that y value change from one to the other? And that's that y2 minus that y1. And then for the run, we do x2 minus x1. Okay? So that's the change in your y calculated over the change in your x. All of these things really mean the same thing. Okay, so when the line rises from left to right, we always read our lines in our graphs from left to right, just like we read English from left to right and numbers from left to right. We start on this side and we go toward the right side. When we look at a line, we're going to read it from left to right. And if it is rising or going upward, we know that that slope is positive. And when that line is falling downward from left to right, that is when that is negative. Okay, so we're going to practice using this that we call the slope formula. In fact, let's label that. Let's box that in here together and say, hey, this is what we call the slope formula. It's the formula we use to find the slope when it's numbers that we have instead of a graph, right? Or maybe even if we have a graph, sometimes we use the slope formula. like right here. There it is. Okay, so describe the slope of the line, find the slope, then find the slope. So first of all, let's describe it. From left to right, do we want to describe this as going downward and falling, or going upward and increasing? Right, this is going downward from left to right and falling, so we're going to describe this as a negative slope. And then to calculate the slope, we're going to do the change in y over the change in x. And I know you could probably use the graph itself and the squares, but let's practice using the slope formula. So follow along with me. Okay, so the slope formula is what we boxed up here just a moment ago. And we're going to practice it here. Now, here's kind of the neat part. It doesn't really matter which one you name your x1 and your y1 as long as you're consistent. So if I want to call, you know, this my x1, y1, and this one my x2, y2, I can do that. Or you could have done it the other way. That's kind of the neat part. It doesn't matter as long as you're consistent. So when we do that y2 minus y1, I might start with that 3 and say, okay, I'm going to do 3 minus, and then this is a negative 2. Well, minus a negative becomes a positive, so don't forget that. Okay. And on my x's, if I started with 3 and I made that kind of y2, then I need to make sure I start with this one. I need to just be consistent on which point I start with. So that'll be negative 2 minus, and then we have a 3 down there. Okay, well, 3 plus 2 is 5. Negative 2 and negative 3 is negative 5. And 5 over negative 5 is just negative 1. So our slope here is negative 1. And there it is. Okay, let's try it for this one. Is it going upward or downward from left to right? I think we can agree that is a positive line. Okay, and then to do our change in y over change in x, we're going to do that y2 minus y1. So again, it doesn't really matter which one you label what. This could be your first point, as long as you are consistent. Okay, so we might say, all right, well, we're going to make this the first point, that the second point. Sure. Then I'll start with y2 minus y1, which is minus a negative, that becomes positive 4, over x2 minus negative 1, so that's positive. So I end up with 4 plus 4, which is 8, 3 plus 1, which is 4. So this line has a slope of 2. So the slope here is 2. Then, this one looks very interesting. When we decide negative or positive here, well, I don't see it going upward or downward. It's just literally, this is a vertical line, okay? Vertical line. This is a tricky one. This guy is always I always call it the black sheep of that linear family, because it breaks all the rules. It doesn't really play nice with most of the stuff we know about lines, and this is no exception. Guys, this has no rise and no run. From left to right, there is no left to right, right? There's just where x was 3. There's nothing happening from left to right, upward or downward. There's only one x value here. This is what we call an undefined slope. Now let me show you why we know that and why that is. Undefined, that means it has no, don't say 0. This is not a 0 slope, okay? This is not a 0 slope. It is undefined. Those two things are very different. Let's see. I'm going to pause this for just a moment.